Good afternoon, everybody. Welcome to exciting afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Hi, everybody. All right. I promised today I'd go through the fats and oils problem set, so I better keep my promise. We'll do our lab today. By the way, good news. Wait, I got the frizzies. There, I got rid of the frizzies. Good news. We're ahead of things. So I'm going to let you out a little early today. You can all applaud. I remember telling you I've been doing extra time on lab days. Normally, if we're face to face, we'd only have 50 minutes of lecture, then go to lab. Because we have an online lab, I can go a little longer. And I did. And that allows me to do more examples, which I think helps you. So, all right, let's get going. Let's do the fats and oils problem set, otherwise known as lipids, fats and oils. Now you can see it's getting toward the end of the semester because Dr. White's getting lazy. What's a lipid? He knows. Thanks, Dr. White. But anyways, what is a lipid? That's a substance or chemical from an animal or anything that was alive or plant that's not soluble in water, but soluble in nonpolar things. Now, name one type of lipid. Well, there's fat is a lipid, oil is a lipid, and a steroid is a lipid. Now, I don't have on here, but I should have. What is a saponifiable lipid? I don't have it, but I should have put that down there. And the answer is a fat or oil. What did I say? What's the sub? Hold on. Sometimes when you do things on the fly, you make a mistake. So I'm going to back up. Norp. That's like if you took a tape deck and backed it up. Most of you have never seen a tape deck. So why did I say that? I don't know. But anyways, I just did a generation gap thing on you. All right, let's do it again. Name one. What is a saponifiable lipid? That's a fat or an oil. What's a non-saponifiable lipid? I give an example. That would be a steroid, or you could put down your hormones. All right, things you should know. What's the difference between a fat and oil? A fat is a solid or semi-solid at room temperature, solid at room temperature, and oil is a liquid at room temperature. Just look at olive oil. It's a liquid. All right, you should know, because I worked in this industry, what's yellow grease, pig's fat. What's white grease? I don't have that down. Pig's fat. What's tallow? Beef fat. So you should know. Tallow is beef fat. White and yellow grease are pig's fat. And when they say white and yellow, that's because one of the important parameters of the different types of fat are color. Do I have time? I do. Let's see if I can find something. There are various color scales, and one of them is important, is called the Gardner color scale. This won't be on a test or final, and they don't have any pictures of this. And let's go back to this. And you can see here, they have different colors, Gardner scale. And I've worked with this, and they have better instruments than they have here. And you compare a sample with the standard instrument, and you can assign a color to that. Another one which is similar, that's used more likely in fats and oils, it's called the Lovibond. And here you have a chart right here of the different Lovibond. And Lovibond actually both get a red and a yellow number from it. And we use that. And there's a third one called APHA, that's for cosmetics. But anyways, we get back to white grease and yellow grease. White grease has a much lower Lovibond or Gardner scale. APHA is only till very light. Example, water, pure water is considered APHA 0. And slightly, so it's really hard to tell without a gauge there. It can go 100, 200 APHA. All right, back to the problem set. All right, let's look at some reactions. Give the organic product or products to the following reaction. And for A, you have this molecule, and you should be able to identify the functional groups. And if we look at this is a triglyceride, one I made up, and here we have 3 esters reacting with sodium hydroxide and water. For test 3, you learn ester, base water, you get back the alcohol and the carboxylate anion of the carboxylic acid you would have used to make that ester. Ester number 1, this alcohol plus this carboxylate anion, you do not lose that double bond. Ester number 2, this alcohol plus this carboxylate anion. And finally, ester number 3, this alcohol, and you get glycerin, and you get this carboxylate anion. Now, with the same triglyceride, if you react with acid and water, as you learned for test 3, I got to write myself a note. Because I forgot to tell you something last time, and I was supposed to remember today. And wrote myself a note so I won't forget when we're done with the problem set. All right, B, we have an ester, triester, triglyceride acid and water. You learned for test number 3, ester reacted with acid and water. Remember, in your stomach, you have hydrochloric acid, H+, and you also have water, I hope you do, and you had an alcohol plus the carboxylic acid you would have used to make that ester. So ester 1, I'll get this alcohol plus this carboxylic acid. You do not lose the double bond. The conditions in your stomach or when this is run will not add acid either as HCl or H+ in water to that double bond. Second ester, you get this alcohol plus this carboxylic acid. Third ester, you get this alcohol and this carboxylic acid. Now, this one, pay attention. We're reacting this triglyceride with hydrogen and a catalyst. Esters do not react with hydrogen and a catalyst. Esters do not react with hydrogen and a catalyst. But double bonds do. You learned that for test 1. And notice I was nice enough to say, look. And what you do is you break the pi bond. Each carbon of double bond gets a hydrogen. Catalyst I didn't write down, but you know can be nickel, platinum, or palladium. And this is the structure you get. Now, If you use a different catalyst, guess what? You get the same thing. Now let's do E. We take that same triglyceride and react it with steam. What is steam? Hot water. As I taught you this chapter or area, you take a ester, steam, same as acid hydrolysis, but you don't need to use the acid because you have the hot water, and you get back the alcohol and the carboxylic acid you would have used to make that ester. And now ester 1 will get this alcohol plus this carboxylic acid. Ester 2 will get this alcohol plus this carboxylic acid. And ester 3 will get this alcohol. So you get glycerin again, plus this carboxylic acid. Now here, I taught you that for yellow grease, tallow, and white grease, we can use the approximation structure right here. R sub S means sterile group with the carbonyl carbon, 18 carbons, no double bond at C9. R sub O, oleal group with the carbonyl carbon here, 18 carbons with a double bond at C9, and once again sterile. And notice my little in-joke SOS, save our ship. And if we add acid and water, when I say react white grease, yellow grease with acid and water, what do you get? Well, it's the same as saying react this with acid and water, triglyceride, acid and water, give you the alcohol plus the carboxylic acid you would have used to make that ester. So ester 1, I get this alcohol plus stearic acid. Ester 2, I get this alcohol plus oleic acid. That's what the R is. Now, let's go back and look at the problem. And says, give the organic product or products for the following reactions. It does not ask you to balance it. So the third ester will give this alcohol plus stearic acid. Now, if you wanted to put a 2 in front of the stearic acid right here, you can. You don't have to, because I'm not asking. Boy, fats and oil workers, thirsty stuff. Now, if you take tallow and add acid and water, guess what? Use the same designation, so we're doing the same reaction, and you get glycerin, stearic acid, oleic acid. If you use white grease, acid and water, the way I've taught it, in real life, it's essentially the same, because the company I work for, Unichem Chemicals, one of the largest producers in the United States of fatty acids, stearic and oleic acid and glycerin, we substituted tallow, yellow grease, and white grease in our production. Whenever our buyer could get yellow and white grease, which is a lot cheaper than tallow, we'd use that. Now, therefore, white grease, acid, and water will do the same thing. The same triglyceride will give glycerin, stearic, and oleic acid. Now, steam, if you remember, you get the same type of products in alcohol plus a carboxylic acid you would have used to make that ester as with acid hydrolysis. So therefore, if I take yellow grease and steam, I'll get glycerin, stearic acid, oleic acid. Same thing with tallow. Now, let's look at K. K is yellow grease, sodium hydroxide, and water. And you have a triglyceride. Remember, for yellow grease, you should know to use this triglyceride where you have R sub S, R sub O, R sub S. Now, you learn for test number 3. Could you hold on? This is an important phone call I have to get. Sorry about that. And the student who just reminded me about the thing I forgot that I wrote down here. Thank you for reminding me. Don't worry that you said a little late. All right, that was my doctor's office uh, working out something. I had to have my cardiologist, because of the problem I had last week, get back to me about, was it all right if I have some dental work next week? All right. Anyways, let's move on. Where were we? We have yellow grease, sodium hydroxide, and water. And if we look at this, what is it? Yellow grease uses the same triglyceride. And you have an ester, base, and water. You get back the alcohol plus the carboxylate anion of the carboxylic acid you would have used to make that ester. So if we look at ester number 1, we have this alcohol plus sodium stearate. Remember, you get the carboxylate anion because the carboxylic acid immediately reacts with the base. Second ester, we get this alcohol plus sodium stearate. Last last ester, I'm getting ahead of myself. My brain does that once in a while. This last ester, you get this alcohol, so you get glycerin, but you get sodium stearate. You want to put a 2 in front of there, you can, but I ask give the products, not balance it. So for that reaction, you get this 3 different products. Now, if you substitute white grease and tallow, you're going to get the same thing. Now, let's do a synthesis one. What do you react with sodium hydroxide and water to get glycerin, sodium oleate, that's the second molecule, and sodium stearate? And the answer is tallow, yellow grease, or white grease, because I'm asking you what's the starting material for this reaction. And you could have drawn the structure, or you could have written down the name. I would accept either. Now, hidden at the very bottom, which most of you didn't see, I bet, what is the surfactant? I didn't even put an answer there, bad, Dr. White. And that is, wow, this is over 10 years old, don't look. Anyways, what is a surfactant? That's a molecule with a nonpolar tail, polar head that interacts with different polar, nonpolar substances. All right, any questions on this? I'm all ears. Yeah. They tell you, I found out years ago, and it's true, as you get older, the one thing that keeps on growing, your ears. Mine were just this tiny. No, not really. All right. Now, a couple of things I forgot when we were doing this chapter that I'm going to do right now. The first one is leaving my class. I expect you to know a couple of things. And one of them is how to describe with words and a general reaction what happens when you eat a fat or oil in your stomach. What happens? I don't know about you, but when I was little, my mother used one time, I was about 3 or 4, maybe 3, because I'd wolf down. I don't know if they still use that term, wolf down your food. I used to really eat fast and everything. And she'd say, chew your food before you swallow, you'll choke. I found out she wasn't lying to me. I did choke. You're wondering, I survived. Well, after you chew your food and swallow, it goes in your stomach. What's in your stomach? Water and hydrochloric acid, H+. And you should know how to describe with words and a general action what happens when you eat a fat or oil. Well, with words, that would be what's the functional group in a fat or oil? An ester. So this is acid. acid hydrolysis of an ester, because that's the functional group in a fat or oil that gets broken down in your stomach. How do you describe this with a general reaction? Well, you learn for test number 3, ester, acid, you can put H plus, or you could have also put HCl. Either one would be correct. Water, and you get back the carboxylic acid plus the alcohol you would have used to make that ester. So, leaving my class, this is important. You should know how to describe with words and a general reaction what happens when you eat a fat or oil. And with words is acid hydrolysis of an ester, because an ester is the key functional group in a fat or oil. And the general reaction is this. Ester, acid, and water, you get back the carboxylic acid plus the alcohol you would have used to make that ester. Now, later this semester, like in the next week or two, I'll also teach you what happens in your stomach when you eat a carbohydrate and what happens in your stomach when you eat a protein. Now, the 3 major food groups. Now, on the problem set, I didn't ask, but you should know I don't know, 3 points each, or maybe even 4 points each. This would be considered a nomenclature question. Draw the structure of stearic acid. And stearic acid is the common name for octadecanoic acid, which I didn't teach you how to go above 10, but that would be the IUPAC name nobody ever uses. And stearic acid has 18 carbons, and the best way to draw it, don't waste your time writing out 16 CH2s, is this. And if I ask for the structure, don't use R sub S. Actually draw it out with the carbons like that. The other one would be oleic acid. And the question would be, draw the structure for oleic acid. I'm going to let you try, and then I'll do it. All right, looks like everybody's done. My turn. And you should know how to draw the structure of oleic acid. And it also has 18 carbons, but it's a monounsaturated acid. And that means fatty acid. That means it has the double bond. Remember, you should know what's the difference between a saturated and an unsaturated fatty acid or fat or oil. It's a double bond. And here's oleic acid. Now, something I just remembered I forgot to talk to you about. Uh, do you people know how to use the emojis like a thumbs up, or if you have your video camera, your webcam, do a thumbs up? Did I talk about Benny Smith in here yet? The company Benny Smith? Thumbs down. Oh no, you're gonna kill me. Thumbs down like in the Roman. No. All right. When I worked at Unichem Chemicals, I was the laboratory manager for all North America. Anyways, and when there was a problem with a customer with their production, I get a call from either the VP of marketing and sales or even the president. You got to be on a plane tomorrow and go there and help this customer out. And I was. Well, one time I got a call late in the afternoon. You got to be on a plane tomorrow morning. We'll get you the tickets and set up the limo. I always, in the chemical industry, whenever I traveled, I'd have a limo pick me up at my home and take me to the airport and vice versa. And anyways, you got to go to outside of Pittsburgh. We'll have the salesman pick you up and take you to this customer. And the customer was Benny Smith. How many of you have heard of Benny Smith? Anyone? Well, they've been bought out by someone else, but you know their product, Crayola crayons. I think you're all familiar with those. And I got to go to their headquarters. This is many years ago. I think they now make them in Mexico, no longer in the United States. But this was outside, I forgot what town, right outside of Pittsburgh, about a half-hour drive. But anyways, went to Benny Smith. When you go in there, the atrium of their headquarters was amazing. They had these big windows, and hanging from the ceiling were different winners of picture or drawings or artwork, however you want to describe it, of the winners throughout the United States. I don't know if they did the world, of at the different age levels or grade levels, you know, grade school, high school, first, second, whatever, of contests they would have using Crayola crayons, and some of them were fantastic. Well, the problem was they had just decided, this is years ago, to come out with 4 different new colors. And part of the test was leave it in a box for a while, come back and look at the crayon. And the tip of the crayons with the new colors were white. The pigment that gives you the color when you write with it had somehow disappeared from the tip. And think about it, a little 5 or 6-year-old kid opening up his new box of crayons, looking for those new colors, and sees the tip white. He'd go to his mother, Mom, these are broken. And Mom would call Benny Smith and not be happy. And Benny Smith doesn't want unhappy customers, mothers or children. So a standard thing in the chemical industry or industries that use chemicals from the chemical industry, when you have a problem and you can't solve it, each of your suppliers, you say, it's your fault, solve it. Well, that's what they did with this. Why did they call me and our company? Because you don't know, a Crayola crayon, this is no trade secret, 50% of the Crayola crayon is stearic acid, which we sold them. And so I went there. I also got to see firsthand, which was amazing, the making the Crayola crayons. It was high speed, amazing high speed equipment. I mean, super high speed. And I worked with them. We I solved their problem. I can't tell you that because I'm still covered by a non-disclosure agreement. It's a trade secret. But anyways, but I got to see that. Next time you look at a crayon, Crayola crayon, half the weight is stearic acid. By the way, the other half is paraffin wax, the same as candles, which if you never ever did in your college days, make your own candles, you take some paraffin wax or stearic acid and coloring, or if you're lazy, you just melt down some crayons and you can make candles, put a wick in there. All right, let's go back to fats and oils, and not fats and oils, carbohydrates. And let's go through this again. We got some time, so I can back up. Remember, chiral object, an object that has a non-superimposable mirror image. Achiral object, an object that's identical to its mirror image. And the thing I didn't do for you the last time, because I forgot, bad Dr. White, bad Dr. White, shame on you, is show you something. Here are objects, but they're also molecules. Now, hopefully you can see me in living color. Well, I just did another generation gap. We look at this molecule, think of this as a carbon in the center, something right here, let's just call it black 2, something here, silver 2, yellow, and red. And this would be its mirror image. If you can see, yellow reflects into yellow, red into red, silver into silver, and black into black. So these are mirror images. If I try and superimpose them, notice the silver line up, the black line up, rods, but not the yellow and red. Well, let me line up the yellow and red. Now the yellow and red, let me hold it from here, line up, but the silver doesn't line up with the silver. So these are mirror images, but not superimposable. So these are chiral molecules. Now, let's think about a few things about chirality in our everyday life. Oops. All right, I'm going to be writing these, and you can get started on it. Which are the following chiral or achiral? An oven mitt with no marking or palms, something special on your palms. All right, next. A right or right-handed baseball glove. Most people use left-handed, but I thought I'd write differently, and I did. All right, let's take a look at this. I'll give you time to work on it. Are the following chiral or achiral? An oven mitt with no marking or special palms, a right-handed baseball glove, a nail like the kind you use for construction or woodwork, and a school bus. Your turn. And I better warn you, I'm going to do some artwork, so don't break a rib laughing. I think I mentioned, speaking every time I say that, I remember about the greatest, funniest movie I've ever seen in my life, Blazing Saddles by Mel Brooks. If you haven't seen Blazing Saddles, you should. Another good one, it's on my list. I don't know if you saw on the uh, front page of D2L for Chem 170. I have a link to my favorite movies, favorite books, favorite music. Did I tell you my real fame to claim is in my senior year of high school, I saw Jimi Hendrix live. Ah, what a concert. What a concert. It was a couple months after his first album had come out. He played Purple Haze, my all-time favorite Jimi Hendrix song, Fire. And, all right, my turn. All right, an oven mitt would look like this, and its mirror image, I'll try and draw it exactly, would be this, and superimposable. So A means without, chiral, you should know, means handedness. So this would be achiral. Next one, as soon as you see the name right or left, you immediately know, just like your hands are chiral, that object is chiral. Now, if you've ever seen a nail, and don't laugh too hard, there's a nail. And here's its mirror image, and it would be superimposable. Something with a superimposable mirror image is achiral. And finally, a school bus. All right, hang on to your hat, folks. Here's the school bus, there's the door, headlights, steering wheel. And if we did the mirror image, what's close to the mirror, you would see in the mirror, closest to the image. Now, remember, a school bus is three-dimensional, and you can't flip it over to make it superimposable. Because if you did, in one, the wheels would be facing down, and the other, they'd be facing up, similar to when I tried to align these together. So, even though it's hard to tell, this is a non-superimposable mirror image. And by definition, something with a non-superimposable mirror image is chiral. And if we were standing right here and I said, we're facing the bus, say the one in America, this one, as opposed to the one in England, the one on the right, I said, for this one, why don't you go on the right side of the bus when we're both facing it? You would know which is right and left. And now let's practice circle the chiral carbons. Remember, a chiral carbon is a carbon with 4 different atoms, 4 different groups, or a combination of 4 different atoms or groups. And D might be a little hard, so don't worry if you're having problems with that. Maybe I shouldn't have put that down, but it's good practice anyways. Let me relaunch the poll. And if you're done, say yes. All right, everybody's done. Let's do this. Now, what's the quickest way? Well, if something has 2 or more of the same atom or group, it's out. If it's in a double bond, a carbon, it's out. So for A, this is out, this is out, this is out, that's out. We don't do oxygen, 2 hydrogen, 2 hydrogen. So we have this carbon left and that carbon. Everybody understand why I eliminated those carbons? Because if you have 2 or more of the same group, you can't have 4 different atoms or 4 different groups on that carbon. Now, if we look at this carbon, it's got a hydrogen, hydroxyl group, methyl, then all this right here. So it has 4 different groups or atoms or combination. If we look at this carbon, it has hydrogen, bromine, methyl, and all that. And guess what? This is chiral. So now let's go on to B. Well, this carbon has, remember, every intersection in a Fisher projection is a carbon here. And if we look at the bottom one, it's out. If we look at this carbon right here, remember, this means this. And in sugar, carbohydrate chemists write their aldehydes this way, synthetic organic chemists like me, except when we're talking about carbohydrates, write it this way. And the carbonyl carbon is double bond to oxygen, so this is out. Now, if we look at this carbon right here, look, it's got 1, 2 bromines. It's out. So that leaves us as 2 carbons, this one and this one. This one has a hydrogen, hydroxyl, aldehyde, and these 3 carbons with the other stuff. It's chiral. This carbon, hydrogen, hydroxyl, these 2 carbons, and these 2, so it'd be OH, H, R, and R prime. it would be chiral. Now, let's finally do D. Now, let me remind you, there are 4 bonds to carbon. We don't write it in. And those are the hydrogens. So immediately I can say this carbon ring is out, this carbon, this methyl, this methyl. They're gone. Not gone, they're not chiral. Now, if we look at this carbon, hydrogen, thiol group, almost said mercaptan, the old name, and then this part of the ring, and this part of the ring. So it would be R and R prime. So it has hydrogen, thiol, R and R prime. It's chiral. If I look at this carbon, it has methyl hydroxyl group, this part of the ring, and you could parse it slightly differently, and this, and they're different. I could have included this carbon in the second circle. Either way, it shows 4 different groups. So that's chiral. And finally, this carbon here, methyl hydrogen, this, and this, and that's 4 different groups. So this carbon would be chiral. Now that one probably is a little harder and I'd never put on a test, but the other ones you should be. Oh no, I just looked at the clock. It's time for a break. And since I had some time today, because we're ahead of schedule, I thought I'd go back and review that and also tell that Benny Smith story. That was really interesting working with them. We used to sell them, this is years ago, I think close to 7 million pounds a year of stearic acid. That went for a lot of crayons. 14 million pounds almost of crayon. That's a lot. All right, let's take a 5-minute break from now. It's actually 1:51, but about 5 minutes, and I'll see you back in 5. We'll do the lab. I'm back. Profound, huh? As you couldn't see. By the way, it's cold out there. I just stuck my head out and arm out to get my mail. It's right by my front door. Wow, it's still winter out there. All right, before we start today's lab, there's one other thing I'd like to do, so I will. And that is leaving my class, you should know let's try this again. You should know how does soap work. First of all, you should know the structure of soap in general. Is a nonpolar tail, and a polar head. You should know water is polar. And we'll learn more about it in today's lab later today. And dirt and grease are nonpolar. And the most important part of the puzzle, how does soap work, is and notice I've gone to a different color and a big font. If we were in a classroom, I'd take up half the whiteboard, like dissolves like. And you should know or be familiar with, and you'll learn it later on in a little while when I talk about it for the lab. That means things that are polar are soluble in polar things. Things that are nonpolar are soluble in nonpolar things. When you try to mix two together, they're insoluble. If you've ever taken and looked at a bottle of oil vinaigrette dressing, the vinegar is mainly water. The oil is vegetable oil. Vegetable oil is nonpolar. Water is polar, and that's why it's separated, heterogeneous. Well, let's look at a particle of dirt. You should know how to do this. Here's a magnified little piece of dirt, say on my hand here, they're clean, but pretend. And you try water, water looks at dirt and says, you're nonpolar, I'm polar, I know likes dissolves like. That Dr. White wrote in real big letters on the screen. I don't know, water, talk about me. Anyways, I'm not going to go down that road. But now if you use soap, soap which has nonpolar tail, polar head, the nonpolar tail, because the like dissolves like, is attracted to the dirt. The polar head wants to stay as far away. I'm only going to show a few molecules, but it totally surrounds the dirt. And we call this, and you should know, a micelle. And I know last time I told you there's no micelles in micellar water, even though they're a good product, I've been told. Now, the micelle now with the polar heads surrounding the dirt on the outside, looks polar to water. And water says to the micelle, I'm polar, you're polar, let's go down the drain together. And they do. If you wash your hands today or anything else, you were making micelles. Did you think about that? You should. So when you clean your hands, your dishes, your car, whatever, your clothes, you're making micelles. When you do your laundry, the laundry detergent is also a molecule that has a nonpolar tail and a polar head, and any dirt on your clothes attracts the soap like that to form micelles and in the rinse cycle down the drain. You should know this. Oh, I better be subtle. Don't you love how I can be subtle? All right, I just wanted to go through that. It's lab time. Let's get to lab. And today's lab deals with what I just talked about, like dissolves like. Now, in chemistry, important rule of thumb, oh, it's on this thumb, can you see? Anyways, a rule of thumb means it's true most of the time. A law is always true. So this isn't always true, but 99% of the time it is. And it describes polar substances are soluble in polar substances, and nonpolar substances are soluble in nonpolar substances. Water is probably the most polar substance in our world or universe. Now, hexane, and you know, 6 carbons with hydrogens on them, no double bonds, is a very nonpolar substance. Gasoline is nonpolar. And this lab, you're going to determine if various substances are polar that you use in your life or nonpolar. And this can be determined by, or this can be accomplished by determining, are these substances soluble in water or hexane? If they're soluble in water, they're polar. They're soluble in hexane, they're nonpolar. Why? Like dissolves like. Now, once in a while, you'll find certain molecules are soluble in both. And you'll find out, did I give you any? And how do you know it's soluble? When you mix two things together, like in a test tube, if it's homogeneous, the same throughout, it's soluble. If you see layers, no matter how small, it's insoluble and it's not soluble. Now, if we're in a face-to-face in a lab, which unfortunately we're not, I would warn you hexane is flammable. We put all hexane waste and the other in the waste beaker, which Dr. Daly, the lab manager, then after the lab, make sure we get collected and they have a waste removal company that properly disposes of those waste. In other words, it doesn't get into Lake Michigan if you pour it down the drain. All right, what's the test? For part 1 water, you're going to put a small amount of DI water. DI water means deionized water, which we have at the labs at ECC. You have special water that you pass through special cartridges that remove any ions, which normal tap water does. And that could play a role, inhibit, or mess up this lab. Now, after you fill it, and this doesn't have to be exact, test tubes are about this big, about a third with water, halfway. Then you put about 10 drops of the liquid. If it's a solid, a small amount, I think they're all liquids, I'm not sure. And you mix it. Now, this is something to teach you. Let's assume this is a small test tube. Never, ever shake a test tube, mix it like this, because you can get chemicals on you or someone else, like the lab, your instructor, lab instructor, me. So never do that. If we're face to face, there are 2 ways you can do it. 1, hold the test tube firmly and hit it 3 or 4 times. Don't tickle it. You really have to hit it. Now, in our lab a couple of years ago, they're called vibro mixers. They're really nice. And you have this rubber disc, and underneath there's connected to a motor in a box. And when you push down on the rubber disc, it starts vibrating way faster than I can. And that mixes up the test tube in like 2 seconds, real good. And I have those out for the lab. Most people use those. But when I wrote this lab originally, we didn't have them. And then you'll wait a minute or two to see if it's homogeneous, the same throughout, or it separates into 2 layers. If it's homogeneous, it's soluble. If it's heterogeneous, it's insoluble. And here are the different ones you would try. Acetone, which you use as nail polish remover, baby oil, ethanol, ethyl acetate, is another type of nail polish remover. And by the way, this, you don't have to draw the structures. Isopropyl alcohol, otherwise known as isopropanol or 2-propanol, is there. Octane, sodium chloride, starch, sugar, vanilla, and Vaseline. And you see where it says do in a beaker? If you get it in a test tube and it's not soluble, it's hard to get out of a test tube. It's easier to get out of a beaker. So for the Vaseline, we do it in a beaker, and vegetable oil. And you see, I already have the data, and that's what you would find. Interesting story. When I first did this lab, there was one other substance on there that Dr. Daly asked, can you please just take that off the list? And that was car wax. And car wax is essentially insoluble, almost nothing. And it's really hard to get off glassware. My students would normally just, oh, I broke it. I better throw it out. We lost a lot of test tubes, and that's why he said, use car, don't use it. So we don't. Now, for hexane, you're going to do the same thing. But now in this test tube, you'll put 1 to 2 milliliters of the hexane. You'll put a couple of drops of the liquid or in a beaker the Vaseline, and you'll mix it like I just showed you. And you'll see if it's homogeneous after a short period of time, all the same throughout, or 2 layers, heterogeneous. If it's the same throughout, it's soluble. If it's not heterogeneous, 2 layers, it's not soluble. And you'll put the waste in the waste beaker, and I remind people that, not down the sink. And here's the results for that same list. And now you can see, for example, Vaseline was soluble in the hexane and not soluble in the water. And those 2 charts will help you determine if something's insoluble or polar or not. Now, after I was doing this, a student came up to me and said, can we try some of our own pairs? Like not just with hexane and water? I said, wow, that's a great idea, which is why I'm letting you know I didn't think of it originally. And what you'll do in part 3 is the first item to be tested, you'll put in the test tube about 1 or 2 milliliters. Then you'll put a small amount of the second one that's in table 3. You'll mix it and see if they're homogeneous soluble. And some of the things are baby oil and vegetable oil, baby oil and starch, starch and vegetable oil and Vaseline, ethanol and vanilla, and vanillin and ethanol and vanillin, and then add some water. Now, why the last 2? If you ever look at a bottle of vanilla extract, which is vanillin in ethanol and water, you'll understand why it helps it make it even more soluble. All right, and then here are questions to answer. Remember, you do not have to draw structures for anything in this lab. And with that, I'm done for today. I'm done for the week, unless you want to stop by tonight for my office hour from 6 to 7:15 on Zoom. If not, I'm going to wish you a good rest of the day, good rest of the week. I'll see you on Monday we'll continue with carbohydrates. We're going to get some neat stuff on Monday, really neat. And with that, I'll say, gang gesund, goodbye. Stole that from Granny.